Hi again. We want to start with another problems on Bernoulli equation application. The water level in the tank is 15 meters above the ground. A hose is connected to the bottom of the tank, and the nozzle at the end of the hose is pointed straight up. The tank cover is airtight and the air pressure above the water surface is 3 atmospheric gauge. When it says it's 3 atmospheric gauge, it means its absolute pressure is 4 atmosphere. The system is at sea level. Determine the maximum height to which the water stream could rise. First of all, we want to make some assumptions to be able to use the Bernoulli equation. First of all, we assume that flow is steady, and so nothing changes versus time, incompressible, and irrotational with negligible frictional effects. So we don't have mixing of the streamlines of the flow. So we can use the Bernoulli equation. So the assumptions that we are making is basically steady and incompressible. The second one is friction between the water and the air is negligible. So we don't have air drag or drag force against the flow of the water or water jet. So we don't have a loss of energy, mechanical energy, as a result of interaction between the air and the water jet. So frictional loss are 0. Friction between the water jet and the air is 0. Is incompressible flow. It means density stays constant and we have a steady state flow. Also, for properties, we assume that the water density is 1,000 kilogram per meter cube. So water density is this, 1,000 kilogram per meter cube. Now, you want to go to the schematic of the problem and see what points we want to choose to perform the Bernoulli equation application. So we take point 1 at the free surface of water in the tank and point 2 at the top of the water trajectory. Also, we take the reference level, it means Z level, 0 level, at the bottom of the tank in here. So this is Z equal to 0. At the top of the water trajectory here, obviously, when the water jet reaches its maximum height, the velocity is 0. So V sub 2 is 0. And atmospheric pressure pertains. So here we have atmospheric pressure. Z1 is 15 meters. P1 gauge is 3 atmospheres. So absolute pressure at point 1 is 4 atmosphere. P2, as I said, is 1 atmosphere, is equal to pressure of the atmosphere. And also the velocity of the fluid at the free surface of the tank is very low. So we assume that velocity at point 1 is 0. Also, velocity at point 2 is 0 because the excuse me, because this is the maximum height that it can reach. So the Bernoulli equation between these 2 points simplifies to this form. Again, I'm using certain form of Bernoulli equation. You can use another forms, another 2 forms. Here, what is the unit of each term in here? The units of each term here is height, so length, P1 over rho g, velocity squared over 2g, z1. All of them have length scale. So this is the Bernoulli equation between point 1 and 2. Now, I also, as I said, know that V1 is 0. Also, V2 is 0. P2 is P atmosphere. P1 is given in the problem. If I rearrange this is what I get. Z2 is equal to P1 minus P atmosphere over rho g plus C1. What is P1 minus P atmosphere is going to be gauge pressure at point 1. Gauge pressure is the pressure at a point minus the pressure of the atmosphere. And gauge pressure is already given, it's 3 atmosphere. I plug in all the values that I have, 3 atmosphere. This is density 1000 kilogram per meter cube, G gravitational acceleration 9.81 meter per square second, times this is the conversion coefficient from atmospheric scale to Pascal scale. This is the final height. This is the maximum height. So the result obtained by the Bernoulli equation represent the upper limit. So it should be interpreted accordingly. It tells us that the water cannot possibly rise more than this value of 46 meters, because this is the upper limit. This is the limit corresponding to having 0 drag force against the fluid flow or the water jet. So we ignored some effects, frictional effect, drag forces. It means this is a maximum value. And in all likelihood, the rise will be much less because of the, again, frictional losses. So this is a maximum height. The next problem is here. So this is a practice problem, and you guys need to, so this is the practice problem, and you guys have to upload the solution to this practice problem on the folder that I will create. I already actually created on Blackboard. So this is your task to do. A pressurized tank of water has a 10 centimeter diameter orifice at the bottom. Where water discharges to the atmosphere, the water level is 2.5 meters above the outlet. The tank air pressure above the water level is 250 kilopascal. This is absolute value, so this is not gauge pressure, while the atmospheric pressure is 100 kilopascal. Ignoring the frictional effects, what is the initial discharge rate of water from the tank? So here we assume that the orifice has a smooth entrance, and thus the frictional loss are insignificant. So let me zoom in this picture a little bit, as much as the space allows me. So we don't have any frictional loss in here. And the flow is steady, is incompressible, and no frictional effects. So Bernoulli equation is applicable. Also, the density that you want to use for this problem for the water is 1,000 kilogram per meter cube. So this is a density that you want to use to solve for this problem. So my suggestion is you take the point 1, you take point 1 at the free surface of the tank and point 2 at the exit of the orifice, which is also taken to be the reference level. So Z at point 2 is equal to 0. And also one other assumption that you may need to make is the velocity at the free surface in here is also 0. So velocity at point 1 is almost 0. And water discharges at point 2 at atmospheric pressure into the atmosphere. So P2 can be known. So P2 is basically sort of given to you guys. So solve for this and upload a PDF file of your practice problem solution on Blackboard. So up to this point, we just talked about the cases where we don't have frictional losses. We don't have any mechanical devices installed in our system. It means we didn't have any pump, we didn't have any turbine, any compressor, any fan, any sudden expansion, any nozzle or diffuser. So we didn't have any mechanical energy added to our flow or wasted or removed from, taken out from our flow. So mechanical energy stays constant, the total mechanical energy, and that's when we can use the Bernoulli equation. He specifically mentions shaft work. When we say shaft work, it basically means pump work and turbine. When we install pump, we are adding energy to our flow. So we are adding mechanical energy to whatever mechanical energy that we already have. When we install turbine, we are taking out some mechanical energy from our flow. So we are losing energy. So we may need to revise our Bernoulli equation if we have mechanical devices and use that revised version of Bernoulli equation. That equation is not going to be called Bernoulli anymore, by the way, because you just added some terms. So let's say there is no heat transfer. You may have some pump or turbine, and also you may have also frictional loss, so pump and turbine. Also, you don't want to ignore the losses that you have between the flow and the walls. In this case, our energy equation, because you remember that Bernoulli equation was another form of, simplified form of energy equation. In this case, our energy equation is going to be in this form. The total initial mechanical energy, if we install a pump in between point 1 and 2, plus the energy that is gained from the pump is going to be equal to mechanical energy at point 2 in this form, plus part of the energy, mechanical energy that is lost as a result of having turbine, part of the mechanical energy that is lost as a result of having some mechanical losses because of frictional loss, because of piping, because of the tubes. These equation, these energy conservation equation is actually for the case of, in the unit of energy per unit mass, energy per unit mass. If you have a flow of energy, you can use this form. So instead of this, if you have flow of energy, you have mass flow rate, you can use this form. You multiply both sides by the mass flow rate. So mass flow rate times the first term, that is the mechanical energy forms, plus the pump. So you see this is lower letter per unit mass. This is upper letter with dot. It means it has a unit of power, is equal to these terms at the second point plus turbine plus mechanical energy losses. Or basically, or also the mechanical energy losses that we're going to talk about in next chapters is mechanical loss as a result of installing pump, mechanical loss as a result of installing turbine, plus mechanical loss as a result of installing piping. But we don't want to talk about that right now. So we're going to look at the more appropriate form of that mechanical loss. This is about the piping, about the tubes, about all the connections, valves and bending, all the connections that are between 2 points. So, and this is the case when we perform the energy analysis in real power plants, because typical power plants has numerous pipes, elbows, valves, pumps, turbines, all of which have irreversible losses. So they impose some losses, some gains of energy to the, and turbines to the system. Also, we can write that equation, our last equation, in another form. So here I divide both sides by the mass flow rate, and also by, so here I divide both sides by mass flow rate and G. So what I get is this. This is the same equation, but in different forms. So the unit again here is different, like what we did in the Bernoulli equation. The units here are lengths. So the dimension here are lengths, like what we had in some version of Bernoulli equation. So again, this is for energy equation, but different units. So this equation and this equation are basically the same in terms of concept, but here we divide both sides by mass flow rate and gravitational acceleration. The units here are lengths. Also, we can interpret that equation using this diagram. How? So this is a mechanical energy flow chart for a fluid flow system that involves a pump, turbine, losses. So let's say this is point 1. Okay, at point 1, we have these 3 terms: pressure term, or flow work term, energy as a result of flow energy, kinetic energy, and potential energy. If you install a pump, basically you're adding some extra because pump add mechanical energy to the system. So it adds to these lines. And when you have turbine, basically you're taking out some of the mechanical energy from the flow, because turbine, when you install a turbine, part of the mechanical energy of the flow is spent to output some work. And when you have loss as a result of piping, also it takes some energy from this total power out of the system. So at the second point, your terms is going to be in total is currently corresponding to these values or to these needs. This is some simulation of mechanical energy flow chart for a fluid flow system. So these some sort of simulations. Now, one special case is, so again, we're going to get back to the Bernoulli equation. Let's say again, you're going to start from this energy equation that we just talked about, and we make some simplifications. We say that there is, or basically, I think we don't have to be worried about this equation for now because we already covered this. Example, hydroelectric power generation from a dam. So here we have hydroelectric. I'm sorry, I have to get some water. So here we have hydroelectric power generation from a dam. Here in a hydroelectric power plant, 100 meter cube per second. So this is volumetric flow rate of water flows from an elevation of 120 meter to a turbine. Where electric power is generated. The